Okay, so thanks everyone for joining today, and apologies for the change of plans. So Carlo got exposed to COVID. I also have COVID right now, so we are the COVID team here. But it's a great pleasure to host today our very own Carl Vondrick. So Carl is actually in charge of data science. He's the data science director as part of LEAP. He's actually the associate professor and an associate professor in computer science at Columbia. He was a research scientist at Google for a little while, and he received his PhD from MIT. And Carl has been very interested in computer vision, videos as well, and how we can actually use machine learning to understand better those different things, especially in terms of vision and video prediction. He's the recipient of the NSF Career Award, which is very prestigious, and it's been funded by multiple research agencies and private companies, including the NSF, DARPA, Amazon, Google, and Toyota. And today he's going to be talking about multimodal learning and how that connects pixels to people. Very happy to have you here, Carl. Thanks.
Thank you, Pierre, for the really kind intro. Yeah, really sorry I couldn't come in person. I really wanted to be in person, actually. It's much more fun in person, but yeah, I didn't want to. I figured it's better to be on Zoom and not spread COVID. So that seems like a no-brainer. So yeah, I might be sniffling a lot throughout the talk. So sorry about that. So yeah, I'm going to talk about, I thought I'd talk about just some general machine learning work that we've been doing. And, also, I hope we can keep it pretty interactive here. So happy to, if you have questions, feel free to interrupt and just ask, and we can have more of a discussion, I think. I think that would be more fun. I'm going to talk about several different things in machine learning that are going on right now that are, I think, really exciting in machine learning. And we can also talk about how that intersects with climate. I think there's a lot of interesting things here that go with climate. So I mean, the obvious thing is that we're in the era of chatbots today. Like, we have these systems that can basically, you can chat with different things, right? You can chat with a document, you can chat with an image. They are really good, right? They know that these boys are eating muffins. They know where these muffins are. They know they're on the table. But they still stumble at these like most basic questions. Like they're not very good at counting for some reason. They can't really count objects. And what's worse is that they often interject their own opinion on things, right? So they hallucinate and make up things, right? So machine learning across different settings, like climate being a big one, is really powerful, right? Basically, you can learn learn from data to simulate what's going to happen. This is an example of some work that we did, just presented in Paris in October about trying to simulate water on a complex surface. And so this is a neural net model that basically, that given the initial conditions, has to roll this out and predict. And so it's really nice for improving accuracy, and also it's way much faster, right? Because it's all learned. And what's interesting is that I can generalize to all these challenging cases with really complex geometry, and really predict kind of how each particle here is going to move. So most of these, like, basically across every situation that we see machine learning right now, are these end-to-end models where, given some input, they have to produce some sort of output, and it's a black box neural net in between. It doesn't really matter what. Often machine learning, we abstract away what the input and outputs are, and just as this black box that maps something from input to output. These systems, while getting very good performance in some cases, have a lot of key limitations that the machine learning community has been talking about for a long time, and the press also likes to talk about this. Like, these end-to-end models are really bad actually at math and logic. They have a really hard time solving those types of questions. They're also not explainable. Like, when they make a decision, you can't understand why they made that output. It's really hard to interpret what's going on inside them, the black boxes. They're often not compositional. They can't generalize to new combinations. If they've seen A and they've seen B, they're not able to usually combine A and B together. There's some examples of this, but it's really unclear when they're able to combine things and when they cannot. they don't have any grounding in the physical world, right? All these models are often trained just in in a computer. They don't actually get to interact with the world. So the grounding and the physical rules that it learns often are wrong, and they hallucinate. They just make up things, right? There's some famous cases where lawyers have used chat GPT in their work, and it turns out that it hallucinates, legal cases that didn't actually happen, right? So we've been developing this approach I'm super excited about, which is basically a system that tries to solve problems by creating a program. It writes its own program, which it can then execute in order to solve a task. And this approach has potential to overcome a lot of these problems here. So if you ask it, if you have this image of these kids again, and you ask it, how many muffins can each kid have for it to be fair? What our approach does is generates this program that breaks it down step by step, which you can then just directly run in order to get the answer. So it breaks it down into, let's find the muffins and count them, find the kids and then count them. And then what's so cool about this is it knows, well, what is fairness here? This is actually a really big topic in machine learning right now, is what does it mean for a machine learning system to be fair? And so what's really interesting is you can actually audit this and understand, why does it think fair, or what does it think fair is in this case? And you can look and directly inspect the code to say, well, fair is an even split, right? Let's just divide the number of muffins by the number of kids. So I call this I think this is a paradigm that's been emerging, where you synthesize a program and then you execute to get an answer. It's not just a black box neural net. There's actually a explicit program that gets generated. And this idea actually is not that new. There's been at least a decade of work in machine learning trying to solve this problem. One of the early papers is from 2015 from neural model networks from UC Berkeley. The author's now at MIT. And basically what they proposed was this type of factorization, where you have a system that first tries to generate program, and then there's another system that actually runs that program. And what was hard about getting the system to work at the time, it was a super cool idea. It just never really worked because it was really hard to train. It was really hard to get a signal basically to learn these different modules. Often require doing RRL, reinforcement learning, which if you ever use reinforcement learning, you know that that's really hard to get working, and just doesn't work very well. So this area basically has been, booming just in the last few years, because these large language models that are trained on code actually can be really good program generators. And so I think this is basically going to enable a new approach in machine learning, where these systems write code that then execute to solve. And you get this explainability, you get this math and logic, you get some grounding in it basically for free. Has anyone read this book, Thinking Fast and Slow? Have you heard about this book? This is a really interesting book from Daniel Kahneman. Yeah, great. And then I think you've heard it. So this is a really interesting book from Daniel Kahneman. He won the Nobel Prize in economics. His career, though, was basically about studying, the human brain and the mind and how it works. Yeah, he's really interesting, a lot of interesting stuff to read. He proposed this idea, basically, that the way your mind works is there's two different systems. There's system one and system two. System one is very spontaneous. It's, things that you don't have to think about. If you look around and see a chair, you know it's a chair. It's fast, and you spontaneously think about it. System two is more slow thinking. So for example, playing chess would be a system two. You got to think things through. So maybe I can, yeah. So machine learning today is actually really good at system one type tasks. We excel at that. Machine learning systems can do an incredible job at system one type tasks. But thanks. Sorry. Yeah. So machine learning does a great job at system one type tasks. But we're not very good at system two type tasks. It's actually systems really struggle. So I think we see this in climate management too. Like there's some things that can just be pattern matching, which might be system one, but there's other things that require AI system to, so to speak, think things through. I should mention this book is very controversial in cognitive science. The reason why it's controversial is it's very hard to get evidence about what happens inside of the brain. So there's very little evidence that this is what actually happens inside the brain. But still, I think it's an interesting framework to be thinking about. So yeah, this type of idea has just been exploding in machine learning in the last few years. 2023 was really a big year for this, and I think it's just going to continue to explode. So basically, the way the system works is a little different from normal machine learning systems because we give it access to a bunch of tools, and the system then learns to combine these tools together in order to solve a problem. So we tell it in computer vision cases. Oh, Courtney, fantastic question I saw in the chat. So Courtney asks, regarding ML and fairness, how is fair typically operationalized by the algorithm? Are there common metrics that tend to be employed? Is assumed to be objective? So yeah, Courtney, this is a fantastic question here. So in this example here, we're able to understand why the system thinks what it thinks the system thinks is fair, which is an even split. But there's many notions of fairness, right? Like, especially like, let's suppose one kid was more hungry than the other kid, then probably an even split is not going to be the right good thing here. So this is ongoing work, is basically how can you better integrate different notions of fairness into machine learning methods. Here this is not really the focus of this. So the main point here is just that you can understand what it thought fair is, at least. There's some transparency into what it thought, but being able to control different notions of fairness is actually very interesting work. And there's not really a solution right now. This is active work in machine learning right now. And I think it's not just a technical question, of course, right? It requires kind of both sides of this, both the technology and this kind of both technology and people to come together to decide what fair is in each case. Okay, yeah, so you give this system a bunch of tools. In computer vision, you give it these tools like finding an object or computing the depth between things. You can imagine any type of tool, right? You could have a PDE solver, for example. Any type of tool you want, right? You can give to this system, as well as a bunch of standard tools in programming languages. So like the ability to do if statements, the ability to do for loops, the ability to sort things, the ability to add and multiply. Basically, you give it access to all these tools, and you teach the system how to use each tool. So you tell it, there's this function find, and what it's going to do is it's going to find something in the image, right, for you. You give it some examples of what that tool does. You can do this for all different types of tools. And what you get at the end of the day for these LLMs is you get what everyone calls the prompt. And this is the worst part about machine learning research right now, is you have these massive prompts to these LLMs that basically explain what are all the tools and how do you use each tool. So it goes on and on and on. But if you give this entire prompt, what you get is this magical system. I mean, the results are amazing here. I really feel like, I don't use this word a lot. I really feel like this is some sort of breakthrough here, where it's able to compose all these different skills and tools together to answer many different types of questions. So if you take an image like this of the drinks on the right, and the question is, find a drink with zero alcohol, it writes a program to break this down step by step. Find the drinks, loop over all of those drinks and look up for each drink which one has alcohol. Ask another knowledge base, does this drink have alcohol or not? And the moment it finds one that doesn't, it's going to return it. So watch this video play a bit, and yeah, so now it found Dr. Pepper. It recognizes Dr. Pepper. It looks up, does Dr. Pepper have alcohol or not? It doesn't, and so that's the answer here, right? So this type of question, what's interesting about this is you can actually look at what the decision-making process is, and you can integrate outside knowledge. It doesn't have to actually learn this end-to-end neuron that doesn't have to learn all of this knowledge. It can actually go out and seek knowledge out on the internet in order to answer a question. The spatial reasoning abilities of these systems are insane. This shows up a lot in machine learning, that these like super simple problems for machines, super simple problems for humans end up being really hard for machines. So, if you want to find the second man from the left here, a lot of existing systems in machine learning actually struggle with this type of question. Surprisingly, it's a really hard problem for some reason. But it's no issue at all for an approach like this. You can write a program, find the min, sort it, and then return this second one. What is amazing about this is it's also consistent. So if you ask for a third man from the left, it generates a very similar program, but then ask for it changes the index, so you get the third man instead. The logic ability of the system is very, very good. So it can answer these type of tongue twister questions. Is the animal that is not gray a dog? Let me think about that for a moment. Is the animal that is not gray a dog? And it can build a program to solve this. It finds all the animals, goes over them, looks for which animal is gray, says if it's not gray, and then once it finds an animal that's not gray, it's going to say, is this a dog or not? What is very interesting about this is basically once the system is able to know what gray is, it can generalize instantly to what not gray is. So like when you teach a kid, a color, they know automatically what not is and what not gray is, right? That's automatic for them. They're able to compose not and colors together, right, to recognize other things. So machines, it's actually really hard. You have to explicitly teach a machine what gray is and teach it what not gray is. So this basically shows an advantage of this, where you get this generalization, this logic of generalization, essentially for free. The math abilities of this are really insane. So you ask it, with the appreciation rate of this car, what will it be worth in five years? It writes out this program basically to calculate this. So finds the car, looks up the name of this car, tries to estimate what the depreciation rate of that car is, estimates what the current value is, and then you can write out the equation with the exponent and the log and everything to get the value of this car to more decimal points than you would ever want, right? So this is something that these feed-forward neural nets actually struggle with. They have a hard time with this type of question because they don't have the ability to do math. They're not able to actually do addition and multiplication. All the operations in a neural net are just matrix multiplications, but that's just how it codes up kind of what operation it does. I can't actually pull out a calculator and do add numbers together and multiply them. So I think for a lot of physics types questions, this is quite bad because these errors are going to accumulate. And I do think that these code generation type of abilities are going to be very important there. Another thing you get, which I think also can have a lot of applications in climate, is you get this adaptive computation essentially for free. So most neural net systems, they really struggle to scale up to very large inputs, right? So if you want to operate on small images, that's okay. But if you want to operate on 2-hour-long video or the Earth, some massive image, some massive time series, it's basically impossible to feed all of this into a single neural net. So what you get with these types of systems is the ability to adaptively basically it's able to do adaptive computation, which means in order to solve all the question, it can shift its computation around inside the input in order to answer the question. So if you ask the question, return the two kids that are furthest from the woman right before she hugs the girl, it writes this program to first go over each frame, asking this question, is there a woman hugging the girl here? And once it finds that, it's going to specialize its computation just to that single frame, right? And so it basically can shift the amount of work it's doing. It doesn't have to do all operations all the time. It can selectively decide what operations it wants to perform at each step. So yeah, we can let this video play out a little bit more. Yeah, so now it found it. It goes backwards in time one frame to do right before, looks for kid, looks for woman, and then answers the question here. Yeah, so yeah, there's a lot of like demos with these big models. We can skip those pretty fast. We basically evaluate this on a bunch of different cases, and you get great performance across the board on these different tasks. So I think this type of framework is really interesting. There's a couple of key limitations here. One limitation is it doesn't have the ability to propagate uncertainty. So yeah, if you take this image and you ask the question, how old are they turning? Well, actually, yeah, make sure you guys are awake. How old is the boy turning? Yeah, 4. Okay, I think I heard 4, right? So right, you count the candles, right? So what's cool is the system can actually build a program to answer this. It writes a program to count the candles, but it gets it wrong because it overcounts the candles. I play this again. It thinks part of the frosting is a candle. So it says 5 instead. Yes, right there. You see it counts part of the frosting as part of the candle. So what's fundamentally going on here is each step of the way, this program has to make a hard decision. Is this a candle or not? And it can't propagate uncertainty. It can't say this is a candle with some probability, 60%. It has to decide. It's a binary decision at each step. So this is a key limitation of these types of systems. And if you could put uncertainty into it, I think it would basically enable a lot more applications. There's a couple different ways you could do this. You could just run the program many times in order to get different answers. You could think of a probabilistic program instead. Like the system could be generating a probabilistic program, and then running the program corresponds to sampling from that program instead. So I think that's quite interesting. You also have a limitation of like sometimes the right tools it needs to answer the question just are not there. So this system doesn't have the ability to read. It can't read text. So when you ask how old are they turning, it actually can't get this right because it's still going to count birthday candles. It can't actually read that there's a 2 and 5 there in order to get the answer. So yeah, so I think this is this type of paradigm of like you synthesize programs and then you run it. I think it's going to be, I think 2024, I'm really excited actually because I think there's going to be a lot more work coming out about this. I mean, there already has been a lot more work just in the first month, 2024, because it just has these intrinsic advantages over what end-to-end models can and do. And what's really wild about the whole thing is these massive neural nets basically are able to write programs that we can interpret, right? These massive neural nets are not interpretable by themselves. They have all these problems, but they can be used to create a program which fixes those problems. So this type of paradigm, I think, is just going to continue to get more and more important. We put all this code actually online. We got a bunch of GitHub stars right when we put it up. So yeah, there's been just a ton of work on this. So I wanted to talk about some more systems, and I think these are also kind of go through a bunch of different systems that are really hot in machine learning right now that I think could have a lot of applications in climate. To motivate this next one, this is a really cute video, basically showing off that the physics abilities of different creatures and different animals are really strong. It's not, we think humans are often really smart, but turns out a lot of other animals are actually super smart. So this example shows off dogs' ability to understand basic physics, which is, when you can't see, when there's an occlusion, you can't see something, a dog still understands that that person still exists, even though they can't be seen. So what happens is when they disappear, the dog freaks out, right? Because it violates their model of how the world works. So yeah, you can find many more funny videos if you want. It's called What the Fluff Challenge on YouTube. So if you Google what the fluff, you just find all these videos of different owners making their dog freak out because they just disappear. So it's a lot of fun. But this is a more general problem, which is how do you get a system that actually can reconstruct things in 3D? So computers are very good at 2D type of data right now, but we live in a 3D world, and so how do you get a system that actually can represent things in 3D? We have two eyes and we get stereo, so we get to see depth with our eyes, but we build up this model in our head about the 3D environment that we're in. So how do we get a machine to do the same type of thing? So the baseline systems at this, were actually pretty good. Like this is a system from maybe 2 years ago that was, given a single image of a chair, could actually reconstruct from 3D the geometry of what the chair looked like. It turns out though that if you so if you rotate that chair slightly, the whole thing breaks, right? It's actually not very robust. The 3D representations are not very robust. And it turns out that we think one of the big reasons why this happens is basically the size of the data. So if you look at 3D data versus the amount of 2D data that you can get, it's just not comparable. So these circles are to scale. I did pi r squared to get the circles to be the right size here and everything. So the big circle on the right is how much 2D data you basically can get on an academic data set. And the small circle on the left is how much 3D data you can get if you just crawl the internet. This was a big effort that we were involved in, trying to download as many 3D models and 3D assets on the internet that we possibly could get. Ton of work went into it, and basically it's only a drop in the bucket in terms of how much data, right? It's just not enough 3D data out there. So these you've probably seen a lot of examples of these diffusion models, which are able to generate images. If you're on Twitter, you see these all over the place now on social media at this point. And these are models that are basically able to, given some text prompt or some input, can generate an image pixel by pixel. And the level of quality and photorealism that they produce is really mind-blowing. So this has just happened in the last 2 years. It just continues to get better and better each time. And it really is an amazing model at doing generation. So these images you see here are just generated. There's not real photos taken with the camera here. So I think this is something that, when we talk about a lot of climate problems, this is something that we should definitely be looking at as a center, I think, is these diffusion models. And scaling these up, because it's just the quality is insane. What's really interesting about these diffusion models is that they seem to be internally learning a model of the 3D world, even though they only generate 2D data, right? They're trained just to generate 2D images, but what we're able to find is that there's somehow a 3D representation that emerges automatically inside these models. So you basically take this diffusion model. What a diffusion model does is it maps some Gaussian noise or some prior distribution to the target distribution, which here is natural images. And once you train that up, you can do a little bit of more training and fine tuning, basically, to teach it how to move the camera around. So you give it some examples of one image from one view and what the camera rotation translation is and what the target view, and you just train it a little bit on that. And you get this model that can do view synthesis. So it can actually predict what various objects would look like if you were to move the camera. So here's just some simple examples, like a shoe and a laptop, right? Oops. A shoe and a laptop. If you want to move the camera just from a single image around, it can actually predict what that would look like. Here's a little bit more complex ones, like a drum set and an elephant, right? It predicts what that object will look like from a different camera view. It's not perfect, right? If you look at the drum set, the circle is not quite right, but it's kind of amazing what this does. What we were blown away by though was uh, that this has the ability to generalize to all these types of scenarios that can't physically be possible. So it works in art, for example. So yeah, this is Van Gogh's Flowers on the left and Pablo Picasso's self-portrait on the right. These are objects that don't exist in the physical world, right? These are not actual objects that have ever existed. They're just a painting, but this type of model builds up a good enough 3D representation of the world that you can actually move the camera and get a 3D model of these objects that don't exist. Um, so, yeah, it works in all types of, it's really interesting. I mean, it just works in all types of cases. Like you can do oil paintings, you can work on cartoons. It works on line drawings, which I find very surprising. These are not 3D objects, they're just 2D, but it still can rotate the camera. It even can maintain the same style, right? So if you have a sketch, it will maintain the same style in terms of this. So, I mean, I think there's a lot of problems in climate that are about super resolution, trying to zoom in or make predictions about things. That's basically what these types of models are, is they're doing predictions. It's just predicting what happens if you move the camera around. So anyways, these are incredibly powerful. If we can take advantage of these, I think it would be amazing. What's really interesting is you get a representation of uncertainty too with these. So here's an example where because it's a probabilistic model, you can sample from it multiple times, and you can get different samples. So I love this example of the camera here, because you don't know how far that lens sticks out from just a single image. And so when you sample from it multiple times, you get many different cameras that vary in how long the lens is, right? So yeah, this is also, for anything in climate in terms of uncertainty, this is really key, right? You can sample many different ones, and it does a very good job. Unlike other types of generative models like GANs, which don't represent the distribution very well, diffusion models do. And so they're yeah, very, very powerful at these types of things. Yeah, so you can turn these into 3D reconstructions too. You can get these 3D reconstructions where you can actually get a full 3D model from these. When we were doing this work, we don't have a lot of GPUs in our group. You need a ton of GPUs to do machine learning research right now. So this is the best that we could do. But what was really cool is we kind of, there's this, machine learning is a very sharing community. We love to share things. So we shared our code, and people online on GitHub just started forking it and improving it. So this is like a person on GitHub was like, okay, they made more GPUs than us. So they went and improved this, and they could get all these different types of results from this model. Yeah, so it's been this big thing. This is something I think we should also try to do in climate is it should be standard practice for us just to share our code and our models, because it just amplifies what your research can do. So like we put this model, we called our model 0123, and we put this up online, and it got, just in a single month, got 140,000 downloads on one of these model sharing websites, and a bunch of follow-up papers came out about it as well. So I think this is definitely a culture that we should try to be building. And the worry about it is you worry about being scooped, right? You worry about you're going to write your paper, and then someone else is you have all these other ideas you want to work on, and someone else is going to come in and just do it for you. But I think that's actually a great thing, because it just means you don't have to do it yourself now, right? You have more collaborators that can help you out and work on your projects. Okay. So last thing I'll talk about is this is kind of a more cool project, but also about, I think it has interesting applications to climate here, and is a different type of model that could be useful. To motivate this though, to motivate the machine learning here, I want to show this example. So this is just an image taken in our lab. There's like this old bookshelf with some mugs on it, right? This is the same image, or sorry, a video now of the same scene taken with a thermal camera instead. And what you see here is, well, actually, I should ask you guys, what do you see here in this video?
Someone lifting up their arms.
Sound lifting up arms, right. So what you're seeing is actually the thermal reflection of someone lifting up their arm. So, right, these objects here, when you go to infrared, actually turn into mirrors, and we can so you can see reflections. What you can do with that actually is you can use those reflections to reconstruct the scene as well as reconstruct the people, even though they're not visible by a normal camera. So this is some work done by a PhD student in my group, Rushi. So it was Rushi lifting up his arms there. So yeah, the principle of this is basically black body radiation, which is precursor to quantum mechanics. It's the idea that every piece of matter produces light. It's just the color or the wavelength basically depends on the temperature of the object. So the sun is really hot, so that produces visible light that our eyes can see. The chair you're sitting on also has some temperature, so it is also producing light. It's just light that your eyes cannot see. People tend to be the hottest objects in our environments. Like we are hot, right? So we're about 300 Kelvin. So we produce infrared light that thermal cameras are able to see. So the military is often really interested in thermal cameras because they can help them see in the night, right? They can see a person at night. Basically, if you have a thermal camera, people turn into light bulbs. And so you can, even when the sun goes down or the lights go off, and under a thermal camera, you still can see people. But it turns out that other things happen too. This is a very interesting modality here. Thermal, like a lot of everyday objects that we don't think of as mirrors actually turn into mirrors. So this window here on the Columbia campus, and actually all windows basically turn into mirrors for thermal cameras. So infrared light doesn't pass through a window; it will bounce off it instead. And so, yeah, many things. Whiteboards turn into mirrors, so we don't think of them as mirrors, but they actually are mirrors. And this is where the applications are here, is cars are actually really good thermal mirrors. So one application for this is for self-driving cars, is if you can reconstruct a person who's occluded behind another car, right? Perhaps you could use some sort of mirror type of scenario in order to sense a pedestrian and avoid hitting them. Okay, so here's where the machine learning. So how do you solve this with machine learning? That's kind of the basic background, but how do you solve this with machine learning? And I think this type of problem shows up in a lot of different cases. This is a general framework we're going to talk about here for various types of inverse problems. So basically, what our problem setup is we have a single observation that we've observed. So in this case, is a thermal image, right? Like this image on the right. And we want to ask the question, what is that 3D world that created this 2D reflection, right? What is the cause of this observation is what we're asking, right? What is that 3D world that created what this image that the camera captured? So we can actually solve this problem by writing down the forward process of how this image was formed, and then we can invert that model in order to do reconstruction. So we're gonna use a little bit of our very basic knowledge of how an image is formed and how light works, and a lot of data and machine learning to write down how did that image on the right actually get formed from this 3D world. And once we write down how that process is generated, we can then go backwards in order to solve different tasks. So I think this is a really, really compelling framework for solving a bunch of different machine learning problems. So in this case, the way this image is formed is there's a 3D world. There's a person, which is a light bulb, is the source of light, right? And there's an object in the world that acts as a mirror. And so what's going on is light is basically emitting from this person. reflecting about the normal on this object where it hits and arriving at a camera, right? So what we can do is we can write down how this image is formed, right? And we can say the way that is formed is there's a generative model of a person. It builds a 3D model of a person given some latent code H. There's a generative model of that mirror given a latent code Z. And what happens is light emits from this generative model, or the object it emits from the object defined by this generative model, reflects off the object defined by that generative model until it arrives at the camera. And so what we want to solve, basically to invert this entire process, is I want to find the latent codes Z and H, as well as the position of this camera, such that when light emits from the person, bounces off the object, arrives at the camera, I get an image that's very consistent with the image that I observed. So yeah, so basically with a little bit of knowledge of how light works, you can do this using on computer graphics called sphere tracing, where you represent objects as a triangle mesh. You find where they intersect. You can reflect about the normal and so on. It won't get into details of this if it's too much. I don't think it's too important. But you basically can then use this to solve different inverse problems, right? It's a framework that allows you to combine data from a generative model as well as a little bit of knowledge of the physics behind it to solve all these different tasks. So here's an RGB image. Here's Rishi again jumping in front of this car, and here's the type of reconstruction that you can obtain. So here's another example. So here's a car, right? Here's the thermal view of this, and reconstructing the person there. So what's actually very interesting about this is it works on complex mirrors. So it doesn't assume the mirror is a plane. It actually can work on any type of surface here. So that's actually very interesting. And yeah, it's actually very interesting. It's really fun geeking out about this because a lot of different a lot of different objects actually turn into mirrors, like bowls and basically ceramics, metal, glass. They turn into mirrors that you can do 3D reconstruction from. Okay, so yeah, I can end there. This is a lot of all this work has been done by fantastic group of students in our lab. It's just been a lot of fun working with them. Yeah, I think a lot of these ideas are kind of a lot of different applications here, and happy to take questions about anything.
Thanks so much, Carl. Okay, we'll leave it out for questions. Any questions maybe online to begin with?
Yeah, go ahead. Yeah, Viviana, you want to go ahead? Go ahead.
Yeah, sorry. Yeah, the host didn't allow me to unmute, so I had
Oh,
to be.
okay. Yeah. Yeah.
So yeah, sorry for not having a video on. Thanks so much, Carl. This was like a great talk. This is actually not a technical question, but I was fascinated by something that you mentioned that is important to me, the fact that we definitely want to share as a community. And I think you mentioned it's great when like people take your code, use it. And I feel like that, I understand, and I definitely share your opinion. I wonder for like the more junior researchers in your group, if you feel like that this could be more of an issue, and how you guys approach this in general, right? I feel like maybe for people who have like already an established position, it's a bit easier to be so relaxed and inclusive, and I think it's a great culture. But I just wonder for like students and postdocs, do they feel the same? Do they feel more threatened? And is this something that you have talked about in your group?
Yeah, that's a great question. I think for junior folks, I think it's great actually, because basically their work gets more known, right? So when people start using it and adopting it, they get the credit actually, right? Because they developed the tool or the finding that allowed all this other work to happen. So I think junior people love this. Like my students and the undergrads and PhD students are always trying to get their code out and promoting it, because it helps promote their own research. So
All
I
right.
think yeah.
No, super. That's great to hear. Sorry, I didn't mean to cut you off, but yeah, just saying, okay, that's great to see that it's actually working. I feel like sometimes we have these fears and they're not necessarily grounded, so it's actually good to hear about your experience.
Yeah, I'd say about like 15 years ago in machine learning, this was a fear, and some people just kind of ignored it and just did it anyways, and it turned out to be great for them. So yeah.
Great.
Hey, I was wondering if you could give us like some more insight into how do you like train that like in your first application, like how do you break down that problem? Like how do you generate those uh, those prompts basically?
Yeah. So this is super interesting. There's a bunch of different ways that you can train this system. The easiest way is through prompting. This is the dirty secret of most machine learning research right now. No one wants to be doing this, but it works well. So you can write this prompt essentially that controls these models. There's basically two principles behind what the way prompt works. There's something called in context examples, which is you give this LLM what are called in context examples, which are examples of input and output pairs. And LLM basically learns to use those in context examples as training samples in order to solve a new task. So there's several papers actually that came out around the same time that show that in context learning causes the transformer inside an LLM to approximate the gradient descent on those in context examples. So this is quite wild. Like this claim is a strong claim, but the fact that there's 3 independent papers coming out with the same result kind of gives some suggest that this could be going on. So in context learning is this way of basically doing gradient descent with these massive models that are otherwise too challenging to train because they need too many GPUs. That makes it possible to train these models. The other tool that you can use from prompting is through instructions. So these models are what are called instruction tuned, which means that they are trained to follow instructions. If you tell them do A, then do B, then do C, that's what they're going to do. So you can formulate instructions in that sense to do it. But I mean, I still think that these are just the beginnings of this. The more advanced version that we're working on and other people are working on as well is how do we actually just learn these programs using using basically an LLM as a generative model. So there's different ways of doing that. Like you could do search through the latent space of these generative models. But you also could imagine Google DeepMind had a really interesting paper where they have a evolutionary method where the LLM does a crossover operation there, and they can show that it can find superhuman programs. So it basically it solved the computer science problem that we didn't know. It was a kind of obscure computer science problem, but it solved all of the computer science program that no one had been able to hand design a method for. So yeah, this is very active area right now is basically how do you integrate these models to do learning on top of them. I think the mistake is to assume that LLMs are only for language. I think that's actually a mistake. These models have more general methods inside of them and can be applied in a lot of different cases. So hopefully that answers your question. Yeah, so and Annette, I see your question on chat, which is how it relates more to climate models. I think all these basic machine learning methods can be used in many different ways for climate. You know, the Earth system, for example, models, those are basically have a bunch of tools, a bunch of different primitive functions that could be composed together. So you can imagine a LLM that figures out how to better compose the existing tools in order to tune the model, right? So I think cogeneration can be huge there. These diffusion models for super resolution, that's going to be, I think that's just a no-brainer in some sense. And you know, it takes there's a lot of details that have to get right for that to work, but it really works well. And these inverting Jernta models, a lot of basic problems in physics and science are about inverse problems, right? And so it allows you to plug in a little bit of domain knowledge about how, you know, this process works, as well as use a lot of data and cleanly combine those basically to solve all different tasks. So, you know, we've been as part of we've been looking at this problem of trying to do simulation. And this is also very interesting work I didn't have time to talk about, but we actually integrate some knowledge basically about how these interactions work, so that it can train on very simple objects and then generalize to much more complex ones. So.
Carl, I think we have one more question in the chat.
Yeah.
Is there anyone else in the room that has a question? Okay.
So can you describe the simulation?
Can you describe the simulation research a little bit more?
Sure. Yeah. This is, so what's going on here is we're trying to learn a forward model, given some complex geometry of a surface, and we have particle representation of a fluid. We want to predict what the fluid's going to be like over different time steps. So this is the graph-based neural net that is basically an autoregressive model rolling out what the positions of each particle is going to be over time. The main innovation here is, how do you get this to work on the interaction between the fluid and the solid when the geometry of the solid is very complex. So we're not talking like just, there's a lot of work about graph neural nets where it works on like a simple plane or a simple curve, but if you want this to work on a very complex surface, it's very hard to get to work, because you have to represent the surface basically with a large number of points, which causes memory to explode and computation to explode. So the main innovation here is showing that you can replace the surface with what's called a signed distance function. So a signed distance function is a continuous representation of the surface. And the way it works is, given some world coordinates x, y, z, a signed distance function tells you how far away that coordinate is from the surface. So if it's 0, you're on the surface. If it's positive, you're above the surface. If it's negative, you're below the surface. So this has a lot of interesting advantages, and you basically can integrate that into a graph neural net, and it can scale up to these very complex surfaces. So this model was basically, this allows you to generalize to cases it hasn't seen at training. So this result you're seeing here, the neural net was trained on very different examples. It was trained just on simple primitives like cubes and spheres and so on, and it instantly can generalize to a complex scene like this. Another interesting thing about this is, so basically this can make it faster, right? Because it can be more computationally efficient to run this simulation out, but it's also invertible. So you can run it backwards if you wanted, and optimize for what is the design, because there's a gradient now. So you can optimize for what is the input that would cause a certain what is a certain input that would cause a certain output to occur.
I think we have one more hand raised in the chat or the Zoom for our last question with the few minutes we have remaining. Linnea, do you want to unmute yourself?
Hi, yeah, thanks, Carl. This is a really interesting talk and stimulated a lot of questions and ideas. One that comes to mind is that we run our Earth system models at 30-minute time steps, but then save monthly or sometimes daily output. And I'm wondering if these methods could be applied to reconstruct some of our sub-daily information that these models contain that we aren't saving right now.
Oh, interesting. I like that idea. Yeah. So you can view these models have really good compression capability. So you could imagine compressing a bunch of data into the weights of a neural net instead. I think that's what you're getting to. Yeah, that's super interesting. So yeah, there's different ways of doing that. Whether they do it with a assigned distance function, it's just the weights of a neural net, for example. There's many different ways that you could do that. But I think that'd be very interesting because instead of storing all the data, you just have to store an implicit model instead that allows you to query for the data at each point, and probably get some interpolation too as well.
Okay, interesting. Thank you.
Okay, Carl, I think we are at time. Thank you for a wonderful talk. It was great to hear about what you've been up to. Pierre, oh, I thought that was a hand raised. Hi, Pierre. So for those of you on Zoom, I'll be sending out a survey for you all to fill out. It just take a few minutes. And for those of you in the room, we'll have lunch in a few minutes. But can we just take another round of applause for Carl for joining us?
Thank you. Thank you.